Okay, so here's where we were last time. We were talking about path independence. And remember, the idea of path independence is as long as two curves have the same starting point and same ending point, then the line integral along the one curve and the line integral along the other curve are always the same. And it's a remarkable property that a vector field could have. And again, I made a big deal about this last time. It almost seems implausible. How could a vector field possibly have this feature, right? But not only can it be done, it is automatically done by a very large category of vector fields, namely gradients. And you just observe, if you have the same starting and ending point, and you're talking about a vector field that's a gradient, both of those line integrals are computed based on only what's happening on the boundary, namely on the endpoints. So if they got the same endpoints, they get the same value of the integral. Who cares what the curve is? Right? It just follows immediately from the fundamental theorem of line integral. So it's a beautiful little connection there. Again, the last thing we talked about was this idea that if you want to rephrase, you can rephrase it as this closed line integral would have to be 0. Right? All closed line integrals are 0. Okay. All right, so that's what we were doing last time. So moving along now. So this is a fun example of the idea of path independence, and specifically the path independence of gradients. So, all right, so let's suppose that we consider what I call the steepness vector field. And so this is just the gradient of the altitude function. Another way to say it is this is the vector field that you do dot products with to detect how much your altitude is increased as you move. It's if you want to know the rate of change of the output, in this case altitude, if you want to know that rate of change over some little displacement, dot product with the gradient, right? Chapter 2, old news. Okay, all right, well, here's the thing. Because it's a gradient, it's also path independent. Because it's path independent, that means that all closed line integrals would have to be 0. Just what we just talked about. All right, fine. So what does that do for us? Well, let's think about the closed line integral in this case of what we call Escher stairs. I don't know if you all are familiar with the artwork of an artist named M.C. Escher. A lot of fun, sort of like geometric contradictions and illusions and stuff like this, and other things, but at the same time, this is what he's most famous for. Well, let me rephrase. This is what I've seen the most of myself. I'm not an authority on this. But so you look at this picture here, and you look at this guy right here, and you can tell what that person is walking upstairs. You can see he's going uphill. Right, just the way it's drawn, shadows and all that. That guy's walking up the stairs. Okay, but then that's upstairs as well, and that's going up, and this whole way, that's all uphill. That's all uphill. That's all uphill. Let's see. That's all uphill. Wait a minute. We're back to where we started. How'd that happen, right? That's the illusion, or whatever you want to call it, geometric paradox, whatever you want to call it. Okay, so I think we all have a pretty good sense that this is some sort of nonsense. There's no physical way that could happen, right? You can't go up, and then immediately upon going nothing but uphill, be exactly where you were previously. Doesn't make any sense, right? So this is the mathematical take on that. And that is, if you were to look at this integral right here, and look at, in particular, look at every little f dot dx, look at every little increase in altitude. Each one of those little f dot dx's, they're clearly all positive, right? So Escher has drawn this in such a way as to make it look like this integral must be positive. But mathematically, because of path independence of gradient fields, we know that it can't be positive. It has to be 0. Right? And so that's how you know that this is impossible. Well, let me rephrase that. Aside from the obvious, this is a mathematical formulation of why Escher stairs are impossible. Everybody with me? Kind of a fun little discussion. By the way, if you've never seen MC Escher before, Google him. It's a lot of fun. There's a lot of neat little artistic, geometric paradoxes and things like that. And he's a very clever, very good artist. One of my favorites. Okay. All right. Now, so let's talk a little bit more about path independence. First thing I want to point out is it's usually more useful as a conceptual tool. Path independence, most of the time, is not so much a computational tool. It's mostly it's a conceptual idea, right? It's a tool for connecting ideas to other ideas. Because let's think about it. From a computational point of view, how would we use path independence? What is the circumstance in which we would use path independence? Well, here's the thing. If you know that your vector field is path independent, well, we already know that means that it's a gradient. But we also already know that whenever you have a gradient field, you can use the fundamental theorem of line integrals, which is a sledgehammer for line integrals. Specifically line integrals of gradients. Okay. So the way I like to think of this is path independence is a hammer, but we already own an awesome hammer. So who needs the two hammers, right? Probably not. Rarely that you need to have a second hammer. We already have a good hammer. So from a computationally point of view, who cares? Now that said, the conceptual uses are very strong. Right? So, for example, if you think about physics, why is it that gradients, in particular, are worthy of the word conservative? Right? What is it about gradients specifically? Well, we talked last time, I think, very, very briefly, and again, this is not a physics class, and I don't want to spend a bunch of time on physics, but what is it that semantically, why conservative? Well, because conservation of energy. Conservation of energy comes from having a notion of both kinetic energy and potential energy. How are you going to define potential energy if the amount of energy that it takes to move along one path is different from the amount of energy it takes to move along a different path? You wouldn't be able to define potential energy at all. So specifically, it's the path independence of gradients that makes gradients naturally understood to be conservative. Right? So again, this is a really useful idea. The conceptual understanding of fundamental quantities in physics comes directly out of path independence. Very useful in a conceptual sense. Okay. Now that said, even though I've basically just said that, who needs it computationally, I'm going to now give you an example of how you can use it computationally. So anyway, here we go. Here's a vector field. Let's suppose we're given that it's path independent. Reasonable gripe could be made here. When is that going to happen? When are you going to just be told? When in the real world, right? Obviously on an exam I can tell you whatever I want. But in the real world, when is it just going to be freely given that something's path independent? That seems unlikely. Bear with me. Suppose we know this vector field is path independent. And I want to move clockwise on the top half of the unit circle, like so. And I want to compute the line integral over that curve of this path-independent vector field. How are we going to do that computation? And of course, you could plug and chug, parameterize, pull back, all that stuff. Okay. Here's the thing, though. It's path-independent. Path-independent means as long as I tie down the starting point and I tie down the ending point, I can take this curve that I was specifically given and I can throw it away. I can replace it with any other curve that I want, right? I could say, I want to use that. Oh man, I did it too fast. I want to use that curve. The line integral over this blue curve is exactly the same as the line integral over that green curve because the vector field is path independent and you can use whatever curve you want as long, of course, as it starts at the same point and ends at the same point. Now, am I going to use this blue curve? No, of course not. That'd be ridiculous. I'm trying to avoid effort, not create effort. I want a more desirable curve, not a less desirable curve. And the most desirable curve in most cases. Between 2 points, straight line. Hard to beat it. Right? Now again, totally free. I can say phooey on this initial curve because of the path independence. And having traded that green curve now for this blue curve, look how easy it is to parameterize. Right? If I did the green curve, I'd have sines and cosines. I'd be doing trig integrals. Nobody wants that. Right? Much easier to deal with this blue curve. Let's get the green curve out of the way. We don't need it anymore. This blue curve, again, easy to parameterize, easy to do the pullback through the parameterization. It's all polynomials. And so much easier calculation. Everybody with me? Kind of a nice example. Now, again, let me quibble with this. But couldn't I still just use the fundamental theorem of line integrals we already observed? And yes, you could. The counter quibble, right, is that even though, yes, I could use the fundamental theorem of line integrals, in order to do so, I would have to figure out what the anti-gradient is. And as of the moment, we have not seen how to do that. Now, we will very soon. Definitely today. Well, hopefully today. So finding the anti-gradient, even though it is typically not that bad, can sometimes be a pain. And there are some examples where finding the anti-gradient is algebraically just going to be prohibitive. And in cases where finding the anti-gradient is prohibitive, this kind of approach, making a path independence argument, changing to a much easier curve where good stuff happens. Look how nice this is, for example. The fact that my curve is entirely on the x-axis makes y exclusively 0, which makes dy 0, which also makes this y 0, which makes that 0. I got a ton of zeros showing up just because I picked a curve that was exclusively on the x-axis, right? So the path independence opens up a lot of opportunities for awesomeness. And it's really nice. So can be sometimes a good computational tool. All right. Is everybody happy? Okay. So how do I know when a vector field is a gradient or not a gradient, namely when it's path independent or not path independent? And there's a wonderful test for this. It's contained in this theorem, proved per what I'm about to walk through with y'all. So here's I want to walk through the argument before I state the conclusion, even though, of course, you can see it right there. Here's what we have here is 5 statements, and I claim that all 5 of these statements are equivalent. So I need to show the equivalence of all 5 of these statements. I'm going to start by observing that we already know these 3 are equivalent, right? Gradients are the same as path independent, which can be rephrased as all closed line integrals have to be 0. So that's just old news. We already know these are equivalent. What I need to do is connect to these other 2 statements over here, and here's the move. There's kind of a couple of moves here. First move, Green's theorem tells me that these closed line integrals can be computed by double integrals of Green's operator. That's what Green's theorem says. So this idea here that closed line integrals should have to be 0, that's literally the same as saying, oh, well then this double integral needs to always be 0. The same statement. Because the closed line integrals are double integrals of Green's operator. Is everybody okay with that? All right. Okay, now let's think about this statement. Let's see here. Let me go ahead and enlarge so we know now that all 4 of these statements are equivalent. Okay, now looking at this statement here, the one in blue, this says a double integral of Green's operator is equal to 0, but wait a minute. This is for all domains D. Let's see here. It's got to be all 2-dimensional domains D, because this statement here is for all closed curves C. So this statement I have in blue is actually a preposterously strong statement. It says this thing, this function that I'm trying to understand here, Green's operator here. Green's operator is a function for which all double integrals are 0 over all domains. Every domain D. How could that be? How could you have a function for which double integrals are always 0? And I think it's actually pretty intuitively satisfying. It's not that hard to believe. There is actually only one function for which all double integrals are 0. Correction, one continuous function. Do notice we are again in this. We've got a regularity cat. I don't want to get bogged down in regularity concerns. But there is only one such function, and that is the function 0 itself. That is the only function for which all double integrals are 0. So, there we go. We've proved the result. And specifically then what we see is, this is what I like to call a local test. It's a local test because if you want to ask the question, is my vector field a gradient? And again, very important question. Knowing whether or not your vector field is a gradient or not tells you whether or not you should try to find an anti-gradient and use the fundamental theorem of line integrals, or is that a wild goose chase? It also tells you whether or not the function's path independent. Really good stuff comes out of knowing whether or not your vector field is a gradient. And what we have now is an answer to that question. Just compute Green's operator. See if you get identically 0. If you do, if Green's operator is flat 0, then yes indeed, you are looking at a gradient. It is path independent. There is an anti-gradient, so you might as well go ahead and try to find it because it's out there. Right? Good information. All right, how we doing? Does everybody see what I'm talking about here? Okay. All right. Now, I emphasize this only works in 2 dimensions. Everything in the argument that we just made here is for 2-dimensional questions, 2-dimensional vector fields. There is an analogous theorem for 3-dimensional vector fields. The analogous tool, the thing that plays the role of Green's operator, is called curl. It's curl. It's our old friend from chapter 3. Now, why is it curl? Oh, okay, we don't really quite have the tools yet, so I can't make this argument for you, but I do think it's nice to note at the same time that while the 2-dimensional local test for path independence is Green's operator, the 3-dimensional local test for path independence is curl. Okay. All right, let's get our hands dirty. Let's do one. Here we go. Here is a vector field. This is you'll note 3-dimensional vector field because it has 3 coordinates. Right, so we're in R3 here. Questions being asked, is this vector field a gradient? Oh, okay, so we're being asked to decide this right here, is our vector field a gradient? And so we're going to use our local test. We're going to compute curl, and then we're going to see if it's 0 or not. All right, and whether or not it's 0, by which I emphasize, I mean the 0 vector, that will answer our question. Okay, so here we go. I'm going to start taking the curl. The very first thing that you get when you do the curl, you got to remember that formula. By the way, reminder, that is one of the things you have to memorize in this class. Most of this class is conceptual. It's mostly concepts that if you really understand them, the memorization is kind of automatic. But the formula for curl, you do have to memorize it. And make sure that you got that locked and loaded in your head and that you can crank it out as needed. So that said, the very first thing you need to compute is the y partial of this, and then minus the z partial of this. And so my first coordinate of my curl, it's not 0. We're actually kind of done, aren't we? I mean, the only reason I care about this curl is because I'm computing it to see if it is or is not exactly the 0 vector. And I already see that it's not exactly the 0 vector. So I don't even have to compute the second and third coordinates. It's clearly not 0. right? And so this is definitely not a gradient. Everybody good? So that's just kind of a nice little hack. I like these little shortcuts when they arise. Now, had we gotten the first coordinate to be 0, then it's not. I mean, it could be the 0 vector. It could be not the 0 vector. We just don't know if that first coordinate is 0. But because it's not 0, game over. Right? Okay. All right. Let's do another example. If I can get this to erase. There we go. What about this vector field right here? And by the way, we've seen this vector field multiple times in the past. That's what it looks like. This is what I like to call the stirred pot, right? If you're looking at a pot of water from above and you've stirred it counterclockwise, this represents the flow of that water in the stirred pot. But, ballpark, something like that. So, question, is this a gradient, we ask? Well, you could try to find an anti-gradient, but your failure to find what you're looking for doesn't really prove anything, right? So we have to use a test. We have a test. Notice that this is a 2-dimensional vector field because it has 2 coordinates. So in R2, our test is Green's operator. You compute Green's operator. It's not 0. And therefore, this vector field is not a gradient. Just a little bit of algebra. Boom. Conclusive answer. Definitely not a gradient. Everybody good? Okay. All right. And then real quick observation. Just looking at the picture, right? Of course it's not a gradient. If it was a gradient, then all of these vectors would be pointing uphill. How could all of these vectors be pointing uphill? If they were all pointing uphill, we'd have an Escher stairs situation. We already know that that's not possible. These cannot all be pointing uphill. That'd be try to visualize. What does the mountain look like where all of these are uphill? It's nonsense. There is no such thing. Okay. All right, so geometric point of view from the sort of the circulation aspect of this, and then algebraic point of view from Green's operator. Okay. All right. Now, what I'm about to show you here is not in the book. This is arguably not new material. This is just a sort of organization, sort of bookkeeping strategy for how to organize the ideas that we've been talking about in your heads. I think this is a really good idea. By the way, I did not really make this up. Where I got this from, and I think this is important to understand both pedagogically and culturally. This comes out of real mathematical constructions. This very sophisticated mathematical constructions, well beyond what we're going to do in this class. And it turns out, you may recall, we've talked previously about differential forms, and there exists this thing called differential forms and integrals of differential forms that are kind of weird notation. They look a lot like coordinate line integrals, and they're seemingly clunky and counterintuitive, but I claim very powerful, and big results come out of it. Well, one of the things you do with differential forms is you make what we call chain complexes and co-chain complexes. And exactly what that is and how you do that is a way more than we can do in this class. But if you take all of that sophistication and strip it down to just, but like structurally, what is it? Just how does it look on the page? And don't worry about any formalities. What you get is this diagram. And I think this is really, really useful. So you may recall I talked back in chapter 3 about composing operators, about taking specifically gradient, and after computing gradient, plugging in your output into Green's operator. And I claimed that there were good things about it, and in particular we talked about the fact that makes an exact sequence. What we mean by exact sequence, you can say this in a couple of different ways. Everything has a lifetime of 2. It's a nice way to think about it. Another way to think about it is exact means that if you have if you have something for which Green's operator is 0, then that means that that thing is the gradient of something else. It's the gradient of some function. And vice versa. Every gradient has Green's operator 0. Everything with Green's operator 0 is a gradient. And so this is a neat fact that these operators connect in this way. And again, we call this exactness. Okay. Believe it or not, the exactness kind of also goes the other way. Now, there is an asterisk here. You notice I say approximately. So I'm going to sweep a formality under the rug. This can be addressed. It's not a problem. I hesitate to even talk about what I mean by this. In fact, I think I'm just not going to. You don't need to know what the format. There is I'm going to commit a little bit of math crime here, and no one's going to catch me on it, so I'm not going to worry about it. Right? But with that swept aside, here's what I mean by the exactness of this sequence. If you have a two-dimensional region and look at its boundary curve, on the other hand, if you look at a curve and look at its boundary points, right? Notice you can compose these boundary operators. If you take the boundary of a region, you get a curve. If you take the boundary of a curve, you get points. They fit. The Legos fit, right? You can compose these operators. This, too, is exact. If you think about it, any two-dimensional region, if you look at its boundary curve, that boundary curve does not have any endpoints. Just think geometrically, right? A two-dimensional region, the boundary curve has to close up on itself. It has to end where it started in some sense. So you get 0 every time. Geometrically, I think that's an interesting observation. And it also goes the other way. This is where the asterisk comes in. If you have a curve whose boundary is 0, in other words, if you have a curve that does not have endpoints, or said differently, if you have a curve that starts and ends at the exact same place, like a loop, that loop is the boundary of a region. It's a boundary of the region that loop encloses. Right? So again, we get exactness. And I'm like, well, son of a gun, that's kind of wild, right? So this is exact, and that is exact. Weird. There's a bunch of patterns that hold when you talk about when you lay things out in this way. And again, you don't have to do this, but this really makes for a nice mental organizational system of how to understand the objects and the participants in the story that we're telling here about line integrals and Green's operator and all that stuff. Right? If you lay everything out on the page like this, patterns are all over the place. So, for example, let's think about the fundamental theorem of line integrals here. Here's the fundamental theorem of line integrals. You could say that what this pattern is that if I look at the boundary of a curve, keep in mind the boundary of a curve is a pair of points, and if I then evaluate some function on those two endpoints, A and B, versus if I take the gradient of that function f that I just evaluated, if I take the gradient of that function f and then do a, take the resulting vector field and the original curve, and if you then do a vector line integral, you get the same thing. Right, so the pattern, roughly speaking, and you thought of it appropriately, is that going to the left on the domain, going to the right with the integrand, the evaluations are the same either way. Now, so what? That's just diagram. I'm just drawing arrows, right? So who cares about all these arrows? Let's look at the arrows for Green's theorem. Green's theorem says if you look at a boundary curve, right, and compute a circulation. In other words, compute the line integral of some vector field over that boundary curve. That's what I have here. Versus, if I were to look at Green's operator of the given vector field and then do a double integral over the initial region of that Green's operator function, you get the same thing. So notice the pattern's identical, right? So the pattern for the fundamental theorem of line integrals is that. The pattern for Green's theorem, my stylus. Pattern for Green's theorem is that. It's the exact same pattern. That's a real eyebrow raiser, right? So there is something unavoidably natural about laying things out in this way, because it diagrammatically makes these two seemingly very different theorems look very related. And by the way, what we're seeing here is a shadow of a very deep fact, and that is that if you take the very sophisticated chain complexes, co-chain complexes point of view on this, and do a lot of math, it turns out that in fact there is a single theorem that represents both of these. They look alike because they are truly special cases of the same sort of like parent theorem called the generalized Stokes' theorem. So this is not a coincidence. This is a glimpse into some very deep realities. And it's also organizationally extremely efficient. So what I encourage you to do, and I'll point out, every time I'm thinking about any of these ideas, anything having to do with boundaries and Green's operators and gradients and line integrals and all this kind of stuff, this is what's in my head every time. I'm always thinking in terms of this pattern because it's so useful. All right. Here's another nice fact, and this is the payoff for this is going to be a little ways down the road, but there are some special vector fields. We've talked about these special vector fields. This is, again, I emphasize that these are the special vector fields. Most vector fields do not have these properties, but there are special ones which you can phrase in various different ways. So one way to refer to these special vector fields we're talking about is that they are gradients. Namely, they have an anti-gradient, aka they're conservative. Right? Here's another way to say it. Another way to say it is that those exact vector fields we just got through showing, gradients are exactly the vector fields for which Green's operator is zero. And we have a word for that. The word is irrotational. If you think about it, Green's operator is a way of measuring the extent to which the fluid has a rotational aspect to it. To what extent are leaves floating in that fluid going to be turning? Therefore, to what extent is the fluid kind of turning and rotating in any sense? Right? So, well, if let's see here. Let me color code well here. If the I'm thinking about the colors. The rotational aspect is understood by Green's operator, and if we're interested in when Green's operator is zero, this zero right here, the fact of the rotational aspect being zero is where the irrotational comes from. Right? So this is very natural terminology. I think this is lovely. I'm a big fan of this idea of thinking of Green's operator being zero as being indicated by the word irrotation. I think it's very geometrically natural. Big fan. Yeah. So, being a gradient shows up on the diagram. Being irrotational shows up on the diagram, and then path independence. And bear with me, I'm gonna mark up this diagram in a way that I this is to what path independence looks like to me. Path independence looks like when you have two curves that have the same boundary points, right? Same starting point, same ending point. Then you get the same value for the line integral. And that's what path independence is. And so this is how, look, it's just kind of intuitive way of thinking about it is that it kind of looks like this on the diagram. So now the payoff for this, the payoff for representing these equivalent properties, again, assuming regularity. I don't want to get bogged down with regularity. The payoff for representing these equivalent properties on the diagram is going to come in Chapter 7, where we'll be able to make arguments about how these simultaneous properties are analogous to some other simultaneous properties that we'll see in Chapter 7, and that's going to take a bit to get to. Okay. Alrighty, the last thing we're going to do is talk about how this diagram can help you solve problems. It was really nice. So let's suppose you've been asked to compute a line integral. Where on this diagram do we see line integrals? Well, here's line integrals. If I'm going to use one of these fancy theorems to compute a line integral, these are they. So, for one thing, that immediately tells me my options. My options are fundamental theorem of line integrals or Green's theorem. Now, which one are we going to use? Well, suppose I wanted to try to use fundamental theorem of line integrals. I'm going to have to take, if I'm going to do this, I'm going to have to take my curve and look at the boundary points, if any. Can I do that? Can I take a curve and identify the boundary points? Yeah, sure, no problem. There's no issue there. Just look at the curve. However, whatever form it's given to you, you can just infer what the boundary points are, if any. The tricky bit, though, if I'm going to use the fundamental theorem of line integrals, I need my vector field to be a gradient. I, therefore, would need to be able to find the anti-gradient. And the diagram, again, helps me see that if I want to turn this expression into that expression, I'm going to need to be able to find an anti-gradient. Now, under what circumstances can I find an anti-gradient? Also represented on the diagram. I just have to compute Green's operator and see if I get 0. Right? So if you want to know if where you are comes from the left, you just move to the right. See if you get 0. Right? So the diagram, just looking at the diagram, actually suggests how to proceed. It suggests what is not an issue, what is an issue in trying to use the theorem I want to use, and furthermore, how do I decide if I can even do the one that is an issue. So that's kind of nice. It's basically telling me that I should compute Green's operator. Okay. And then likewise, if you want to use, if you want to go the other way, a lot of little things to delete here. Okay. If you want to use Green's theorem, let's say, how would I decide if I can use Green's theorem? Well, one thing I'm going to have to do, whatever my vector field is that I was given, I'm going to need to be able to compute Green's operator. Is there any impediment for me to take a given vector field and compute Green's operator? No, this is not hard at all. Compute a couple of partial derivatives. Just follow the formula. There's no challenge in computing Green's operator. But I'm also going to need for my curve to be a boundary of something. Said differently, if you'll allow me a little bit of linguistic flexibility, you need to find an anti-boundary. I like that term, anti-boundary. The book doesn't use that term, but it makes sense, right? It's the thing whose boundary is what you started with. So the question, the sticky wicket of whether you can or cannot use Green's theorem, being whether or not the curve is a boundary of a region. You can see it on the diagram. You can see that you have to move backwards through that arrow. And it also, again, suggests a way of arbitrating this question. Is my curve, does it bound a region? Does it keep the cows in the pen, right? Does it close up? Well, that's true if and only if it starts at the same points that it ends. Namely, if it doesn't have any actual true boundary points. So the diagram, again, tells you what to look at to make the decision. A lot of good, useful benefits from thinking about these objects and these kinds of questions in this context. Okay. All right. How we doing? Is everybody on board? Okay. So lastly, let's talk about how to find lastly for this chapter. How do you find an anti-gradient? Now, I've been kicking this can down the road for a while now, right? Long ago, as in, well, let's see, not that long, but yesterday, I guess it was, right? I observed that the gradient of this function is the vector field we were given, but I gave no indication. How did I know to think about that function? Did I just pull that out of a hat? Did my inner oracle tell me x squared, y squared must be no, right? There's got to be some method. What's the process by which I take a vector field and infer what the anti-gradient is if there is one? Right? Very important question to address. Okay, well, here we go. If I have a vector field that has coordinates, PQR, again, pretty typical. You can call them F1, F2, F3 if you want. PQR kind of rolls off the tongue a little nicer. If I want to know if it's a gradient, well, here's what a gradient looks like. Gradients are made up of partial derivatives of my alleged anti-gradient, right? This mystery function that I'm trying to find. So, all right, well, if I want this to equal to that, that just means that I need for this to equal to that. In other words, I need for all three of those coordinates to equal to each other, right? All three. P has got to be partial of f with respect to x, and Q has got to be partial of f with respect to y, right? If you have two vectors that are equal, then their coordinates are all equal. So, the way that I decide then as to whether f is a gradient is by trying to find a function f that satisfies these three equations. And now let me rephrase that. I need to find a function f that satisfies these three equations. It's the exact same three equations, asterisk, math crime, confession to come. Because if you think about what this says, that the partial of f is p. This says f is the anti-partial of p. It's the same statement. It's like active tense, passive tense, or grammatically different, but they're morally equivalent statements. Okay. And in particular, the way that I turn this statement into this statement is I just take the partial with respect to x on both sides. And you take that partial of the right equation, it turns into the left equation. All right, now let me confess to the math crime. Of course, when you take an antiderivative, there's always a constant. Why do we add in a constant? What's the deal with this plus c? The whole point to a plus c is that when you do that partial derivative, it turns into 0. Right? And so this is just single variable calculus, but any constant, its derivative is 0. And so you can kind of, in some sense, you can add in any constant over here and it's still a perfectly good anti-partial and there's really not a problem. So here's the twist. What is different about this in multivariables, keep in mind, going this way, I'm taking a partial with respect to x, and constants are not the only functions whose x partials are 0. Any function that doesn't have x's in it, anything that's just a function of y and z, also has x partial equal to 0. So also perfectly fine to add in on the right-hand side. And remember, you can't just go around assuming that whatever was the most convenient antiderivative to write down, that must be the one you're looking for. No, there's a bunch of them and you have to entertain all the possibilities. Right? So here, with the x antipartial, you have to add in a yet unknown function of y and z. And for the y antipartial, you need to acknowledge a yet unknown function of x and z, etc. Okay, so what you really need then is you need these three things to all be equal. And this is the tricky, but this is where the game begins. You have to write it down and play the game, try to figure out what these functions might be that make these things all equal to each other. And it's just a matter of writing it down and playing the game. There's really not that much to the game. It's a pretty simple game to play. So again, let's go ahead and do it. We have to take the x antipartial of the first coordinate. We have to take the y antipartial of the second coordinate and the z antipartial of the third coordinate. There we go. These are my antipartials I need to compute. So I got to compute these antipartials. They're just polynomials, nothing to it. There's my easy antipartials, right? You got to make sure you can do it. Watch out for the details. Therein lies the devil. It's you got to be careful. Don't forget to add in your what we call partial constants, appropriate to which partial derivatives you're taking. And now begins the game. Can I make these things all equal to each other? Now, I emphasize, at a glance, you look at these three things and you think these are clearly different. They're not the same. What are we even talking about here? Again, that's not the question, right? I'm allowed to have these partial constants in there. I can pick whatever I want for these C1, C2, C3 as long as they're only functions of what it says they're only functions of. And so, so I've got a certain amount of flexibility. I've got some wiggle room here. I might win this game yet. Right? So here we go. Let's try to win the game. I see an x squared y there. I see an x squared y there. I'm kind of hoping that in the final thing that these are all equal to, I feel like I'm going to need an x squared y. But my problem is, where in here do I see x squared y? It's not that. It's not that. Ooh, you know what? Maybe it's in here. Maybe x squared y is this function of x and y. This is allowed to be any function of x and y. Anything that I want. And I tell you what, I want it to be x squared y so that I can say, yeah, all of these expressions have the term x squared y in them. Does that make sense? And you keep going. So let's see here. We have xz and xz. Kind of feel like there ought to be an xz. Where's my xz? It's not there. It's not there. Oh, wait a minute, though. Maybe xz is what that is. Again, cool. Now I've got xz in all of my terms. And then likewise, minus yz squared, minus yz squared. And this could be minus yz squared. We just won the game. All three of these expressions are all equal to that. So this is an acceptable gradient. Everybody see how this works? So, see what I mean? It's not that hard of a game. You just have to think strategically about what your constants on the right, your partial constants on the right ought to be, and just try to cram it in, try to make it work. Try to fit it in. And in this case, it works. All right. Reminder, though, it shouldn't always work, right? I mean, we know that there are some vector fields that don't have an anti-gradient. There should not be an anti-gradient for this one. We've already computed Green's operator. It wasn't 0. We know there is no anti-gradient. And in a situation where there is no anti-gradient, we better hope that our method doesn't find one, because then we can't trust our method, right? It better not find something that doesn't exist. So let's see what this looks like. How does the game play out? Well, these are your anti-partials. Those are those antiderivatives directly. Here's your partial constants. Here's the game then. I need to find something that's equal to both of these lines. And you're going to lose this game. This game is stacked against you. There's no way. How could you possibly have a function of only y here and a function of only x here that would make both of these things equal to each other? And it's just, you can't do it. Everybody see how you lose before you even start. It's a no-win game. And so good. That's how it ought to play out. Right? Because we already knew that there was no anti-gradient. Okay, so we are now done with 6.3, and we'll pick up with Chapter 7 on Friday. Y'all have a good one. See you later.